Everybody, I'd like to give you a quick introduction to the idea of characteristic impedance as it pertains to transmission lines. So you notice I've written down the telegrapher equations here. So here's the voltage derivative and then the current derivative over here. And for the sake of argument, let's just imagine what would happen if I had a single wave traveling to the right. So I'm going to write a general solution for that. So V of z is equal to V naught plus e to the minus gamma z. All right, so remember, this represents a wave propagating down a transmission line into the positive z direction. Okay, so positive z like that. So just some voltage wave like so. Now remember, if I am given a voltage wave, I am not necessarily free to choose some arbitrary current. Like there is only one and only one current that can go with this particular voltage here. So what I'm going to do now is take this solution, which we know satisfies our wave equation, but I'm going to plug it back into here and to see what kind of current must correspond to this voltage. So I'm just going to take the partial derivative with respect to z of this term here. So V naught plus e to the minus gamma z is equal to negative r prime plus j omega L prime times my current. So this derivative, you notice it's only going to act on this exponential here. So I'm just going to get the following. V naught plus negative gamma e to the minus gamma z is equal to all of those same things over there. Now, all I'm going to do is solve for current by just dividing this term out here. So we're going to do a little bit of algebra, and we find that the current as a function of z is equal to the following. I get V naught plus gamma divided by r prime plus j omega L prime. So that's an L. And there'll be this e to the minus gamma z over here. So you look at this, and this has the form of essentially I naught plus e to the minus gamma z, just like we expected before. So we know that this kind of a current here is a solution to my wave equation here, and I know that this voltage is a solution to my wave equation, but now I have an expression that ties the two together. So if I am given one, I now know exactly what the other one will be. So what I can do now is I'm going to solve for I naught plus, or I can solve for I naught plus, and you notice it'll just be some fixed ratio over here. So let's do that real quick. I'm going to say I sub 0 plus is equal to gamma divided by r prime plus j omega L prime times V naught plus, like so. Okay, so given some voltage amplitude here propagating down a transmission line, if I multiply it by this particular parameter here, I know what the current is. Or vice versa. If I'm given the current, I can then solve for the voltage by dividing this thing out. So this particular parameter here is just determined entirely by the geometry of the transmission line itself. So what I'm going to do now is simply calculate this ratio here of V0 plus over I0 plus, and what you'll find is you get the following value, r prime plus j omega L prime divided by gamma. So this thing here is extremely important in transmission line theory, and we're going to even give it a name, z sub 0, or simply z naught, and that is called the characteristic impedance. Characteristic impedance. Like so. So you notice, in a way, if I know the characteristic impedance of a transmission line, then I know that this ratio must always be a particular value. So if I'm given a voltage, the current is determined by that characteristic impedance, and sort of vice versa. So what happens is eventually you kind of stop thinking about transmission lines in terms of their voltages and their currents, and really this thing here is what determines all of the fundamental behavior of a transmission line. I should say all of the action is kind of contained in this term here. Although this expression here is not entirely useful, so we're just going to do a quick little substitution. Remember that gamma from our previous lectures evaluated to the following: g prime plus j omega c prime, and the whole square root of that. So that was what gamma evaluated to. So if I substitute this gamma, this value, into here, you get a much simpler expression for z naught that contains all the explicit information we care about, and you'll get the following. You get an r prime plus j omega L prime divided by g prime plus j omega c prime square root. Okay, so this is what you get if you plug in and do a little bit of a simplification. All right, so that little parameter is going to mean a lot moving forward with transmission lines. And in particular, there's one special thing that's going to happen. We're going to talk about the lossless condition, where r prime is equal to g prime, which is 0. So that is lossless. Now, transmission lines are generally not lossless, but they are low loss enough that you can generally make this approximation, in which case you'll notice that my transmission, or my characteristic impedance, simplifies greatly, which just becomes the square root of L prime over C prime. So this is also an extremely common expression, and it's generally more appropriate to use this expression over here than this one over here. That's because the R and the G are generally much, much smaller in comparison to L and C. And if these terms were big and dominant, then you wouldn't have a very interesting transmission line anyway, so we tend to not care so much about the general lossy case, but we like to think more in terms of the lossless case over here. So the inductance and the capacitance per unit length fundamentally determine how voltage and current will relate to each other down a transmission line, which in a way is all the information we really need to know about the fundamental behavior of a given line. It's all contained in these little parameters here. Now, just a more general thought I want to leave with you is this notion of impedance. Okay, because it's not really a lumped, you're used to thinking of this in terms of a lumped circuit element, right? So you imagine something like a capacitor here in parallel with some resistor here might have some lumped impedance Z, right? And you learned that in circuit theory. But more broadly speaking, it's more useful to think of impedance as in terms of this thing over here. This ratio of voltage to current is really the thing that defines what impedance is all about. And you've encountered this notion before. For example, you remember from 3300, electromagnetic field theory, you had an electric field divided by the magnetic field, the auxiliary magnetic field, and that gave you this thing called an intrinsic impedance. So in fact, if I had an electric field and a magnetic field propagating through free space, you would have an intrinsic impedance of free space that evaluated to mu naught divided by epsilon naught. So you can see how that notion of impedance isn't really about loss of energy or storage of energy in these lumped models, but it's really more of the ratio of voltage to current, or electric field to magnetic field, in a more broad sense of propagating waves. So it's common to hear words like a high impedance wave might be something with a very large magnetic field component divided by the, or you could say the magnetic permeability divided by the permittivity would create a high impedance wave, or vice versa. If I had a very large dielectric constant, I might get something like a low impedance wave. In a sense. It's just talking about the ratio of the E to the H field. So just think about that in terms of a more broad philosophical sense, that this idea of impedance means a lot more than that lumped circuit model here. And the characteristic impedance of a transmission line is really going to tell us a whole lot about how these lines behave, especially when you have transmission lines encountering lumped loads or transmission lines connecting to each other with different impedances and so on.